Hi guys, it's Mr. Rocco. This is video to start topic 2, which we are going to start this week. This is the week of October 5th. Let me just do a quick breakdown of this week. So there is a test that you need to take on topic 1 that is posted Monday morning at 8 a.m. on Canvas. It's 28 questions. Most of them are multiple choice. There's one or two, actually I think 3 short answer questions. But anyway, that's on Canvas. That test needs to be completed by Friday, just like any other assignment, 3 p.m. The lab that you need to finish or complete by Friday, also this Friday, is lab number 2. That is the graph analysis lab. Again, the graphs are done. You just have to do the answer the questions, analyze the graphs, do the questions, do the vocab. That's due this Friday, which is October 9th by 3 p.m. Then I'm going to be making this video, so please watch the whole video in its entirety. Pause, rewind, go back if something doesn't make any sense. And then also, after you watch the video, complete the assignment. It's called Spheres of the Earth worksheet that goes with this video. So you've got topic 1 test to do this week. You've got lab number 2, the graph analysis lab, to complete. You've got this video to watch, and you've got another assignment to do that goes with this video. All that's due by Friday, 3 p.m. Okay. So let's jump right into topic 2. Topic 2 is called Measuring the Earth. It is also chapter 2 in the review book. So if you get confused or something doesn't make any sense, use chapter 2 in your orange covered review book to help you understand the material if this video is a bit confusing to you. So we're going to start out with this in this unit with the spheres of the Earth. We're going to go through the atmosphere, hydrosphere, and lithosphere. So let me pull that up. The biosphere is also a sphere. I don't cover that. That's living environment, or they used to call biology. That's why it's bio, which means life. So that is going to be all your living organisms. That's covered across the hall when you get to living environment. I cover hydrosphere, which is water. Atmosphere is the air you breathe. Most kids know hydro. Well, at least they know the atmosphere. Hydra, most kids know that as well. The one that they don't know is called the lithosphere. So lith, the prefix lith, L-I-T-H, comes from the word for rock. The way I remember lithosphere is it's land. So the land that you stand on is the lithosphere. L for land, L for lithosphere. So if you remember land is lith, that'll help you. L for land, L for lithosphere. So let's start with the lithosphere. So it's the outer layer of rock that forms the outer shell of the Earth. So the outermost layer of the Earth is called the lithosphere. It is about 60 miles thick, which is 100 kilometers. And the upper portion of the lithosphere is called the crust. So there's actually 2 portions to the lithosphere. The upper portion is called the crust. Let's go right to the ESRT. So this is on page 10 in your ESRT. So you should take this out and take a look at this. I'm going to just pause for a minute while you get your reference table out. Okay. Or you could pause the video. Here's the word lithosphere. I'm going to circle that. And then you see there's a bracket right here. It covers both parts of the lithosphere. So there's 2 parts. This thin black line on the top is called the crust. It's right there. And then this thin white line under the crust is called the rigid mantle. Rigid means solid. So you've got crust and rigid mantle that both make up the lithosphere. There's 2 types of crust, and that's listed over here in this density chart. This chart lists density numbers as you start at the surface and as you go this way down to the center of the Earth. So the center of the Earth down here where I'll make this dot. Notice the densities, which we just covered density in the first unit, how many grams per cubic centimeter. It's 2.7 to 3, then it goes 3 to 5, 9 to 12, 12 to 13. So it gets more dense, it becomes more dense as you go inside the Earth. The crust is made of 2 types of crust: continental crust, oceanic crust. Continental crust obviously means your continents: North America, South America, Africa, Asia, Australia, etc. The bedrock below us is made of mostly granite, so it's called granitic crust. You see the word granitic right there. Ocean crust is made of a rock called basalt. It's a darker gray rock, fine grain. We'll get into rocks in the spring. We'll look at rocks in detail. But if you were to go down to the bottom of the ocean, dig through the sand, and then you hit the bedrock under the ocean floor, that's basalt. If you dig through the rocks here on land, and again, most of our surface of New York State is covered with sedimentary rocks. Granite is an igneous rock. And again, I don't remember how much you remember from igneous rocks, or rocks in general when you covered them in middle school, but you have your igneous, your sedimentary, your metamorphic. So the rocks on the surface here are sedimentary. Sandstone, shale, limestone, those are sedimentary. Granite is an igneous rock, so that's below us. That's what makes up our bedrock, our foundation. Anyway, so those are the two types of crust. And then the mantle is broken up actually into three parts. The lithosphere contains the rigid mantle, that thin white line right there. Then there's two other parts to the mantle. There's this plastic mantle, which they call the asthenosphere. The asthenosphere, when they say plastic, they don't mean plastic like you think of the material plastic. Plastic means it's not solid, it's not liquid. It's kind of a in-between. It has some flow to it. It moves. And you can actually see that. They show it to you in these arrows. So I'm going to circle them right over here. So this is what they call convection, like a convection oven. If you have a convection oven, there's a fan in the back of your oven. That fan's purpose is to circulate the heat around in a nice circle in the oven to cook your food evenly. And that's what you see here. Convection is a circle. So you've got these arrows over here on the right are going around and going clockwise. These arrows on the left are going around and going counterclockwise. And what that's doing is right here in the middle is taking the crust of the earth and splitting it in two different directions. The right side is going to go to the right. The left side is going to go to the left. And again, we'll cover this more in the spring. That's called a divergent plate boundary. In this case, it forms a ridge down the middle of the Atlantic Ocean. The ocean floor will split and get bigger. So that's what's happening in the plastic mantle. It's called convection. That's what drives plate tectonics. If you've ever heard of plate tectonics and the continents drift apart, and you've heard of Pangea before, that's the driving force that causes plate tectonics, is this convection in this plastic mantle. And then underneath that, you've got the rest of the mantle, which is the majority of the mantle. The thickest part is called stiff mantle or stiffer. That's going to be back to solid again. So you've got this rigid mantle, that thin white line, which is solid. You've got this plasticky, again, not solid, not liquid, kind of in between. That's the asthenosphere. And then you've got the stiff mantle here. Once you go to the middle, you got your core of the Earth, which is made up of two, outer core, inner core. Outer core and inner core both made of iron and nickel. You see it's written right there. The only difference is the outer core is in a liquid phase. The inner core is in a solid phase. And again, we'll cover that more in the spring. The idea is they know that that's solid, because kids are like, how do they know that that's solid and that's liquid? Studying earthquake waves. And again, I don't know if you covered this in middle school. I think you might have. There's called P waves and S waves. P waves can travel through anything. S waves can only travel through solids. So studying earthquakes and earthquake waves, when earthquakes give off these seismic waves, that's how they've been able to determine that the inside the Earth there's a solid inner core and a liquid outer core. Anyway, so your job is just to remember for now the lithosphere. So the lithosphere is the crust and the rigid mantle, the thin black line and the thin white line. This picture shows the same thing. So you've got the crust on the top. You've got that rigid upper mantle here. You've got the rest of the mantle here. You've got your liquid outer core here. And you've got your solid inner core here. The best analogy I use for when I talk about the Earth, I think of an egg, a hard-boiled egg. So if you take an egg out of the fridge, hard-boil it, and then open it, you'd see the thin shell of the egg is like the crust. So the crust is very, very thin compared to the rest of the Earth. Think of it like the shell. The egg white would be like the mantle. And then the yolk in the middle of the egg would be like the core. All right, then we have Hydrosphere. So Hydra, oops, fix that. There we go. Hydra meaning water. So if you go for a jog, go for a run, but you forget to bring water with you, you become dehydrated, right? De meaning without water. And so you got to hydrate yourself. So it's all the water that rests on the lithosphere. So it's all the different types of bodies of water, from your little creeks to your big rivers to your lakes to your oceans, etc. So it's lakes, oceans, rivers, streams, etc. The Earth has a nickname. It's called the blue planet. The reason it's called the blue planet is because obviously it looks blue. If you're standing away from the Earth, if you were, let's say, on the moon and you're looking back at the Earth, it's 70% of the Earth, roughly, is ocean. And so that's why Earth was given a nickname blue planet. Looks like a big blue marble. So not only we have oceans, you have your lakes, you have your rivers like the Hudson, you have your streams, creeks, all that stuff. That's all part of the lithosphere. Excuse me, hydrosphere. Let's get that right, Mr. Rocco. Hydrosphere. You can go to college and you can become a hydrologist. So it's a degree you can get. You can get your degree in hydrology, and then you can have specific parts of that. You could be a person who studies the Hudson River, or you could be somebody who studies the Atlantic Ocean, or you could be somebody who studies the Great Lakes. I mean, you can really get into just a specific career. But yeah, you can go to college and become a hydrologist. Of all the water on Earth, let me pull these boxes away. All the water on Earth, about 97% of it is salt water. Only 3%, and this is where the problem comes in. People say, well, Mr. Rocco, we have so much water on Earth. Why do I have to worry about shutting off the water when I brush my teeth or conserving water? That's because 3% is fresh. 97% is salt. You can make salt water into fresh water. There's different ways of doing it. We'll talk about this later in the year when we get into the water cycle. The most common way is what they call reverse osmosis. They pump the salt water through a membrane, semi-permeable membrane. It filters the salt out. There are many countries that do this, especially your drier countries. Middle Eastern countries like Saudi Arabia and Israel have to do this. There's quite a few states in the United States that do it. Florida, Texas, California. Those are three states in particular that do have to do reverse osmosis. It's very time consuming. It's very costly. The price per gallon is probably double, triple, I think, what it costs for normal just pulling out groundwater out of the ground. So it is a very costly process. The U.S. Navy does reverse osmosis when the ship goes out to sea for months and months and months. It's not that there's a Poland Spring guy coming up every day dropping off water. They have to get their water from somewhere, so they pull it out of the ocean and they process it through reverse osmosis. They can make quite a bit of water. I mean, I forget the number, but they make thousands and thousands of gallons a day. But yeah, only 3% of the water on Earth is fresh, naturally. The ocean crust is your thinnest part of the crust. So continental crust is much, much thicker. That's your mountains, right? Think of the Rockies, the Appalachians, the Himalayas, Mount Everest. Those are going to be much, much thicker layer of the crust. The ocean crust is very thin. Ocean crust is only 3.8 kilometers, which is roughly like a mile and a half. So a lot of your drilling, when they drill for oil and natural gas and your resources, it's not that they don't do on land, they do, but a lot of it's done offshore. So a lot of your oil rigs are set up in places like the Gulf of Mexico or off the North Atlantic or North Pacific, where they have these big rigs out there that don't have to go very far. They go through this thinner ocean crust and they're able to get down to the oil and the deposits they need, the resources, because it's much, much thinner. This is just a breakdown of the distribution of water. So 97% of the water on Earth is salt, saline. 3% is fresh. Then you take that 3% fresh water and you put it into this middle column. Of the 3% that's fresh, almost 70%, 68.7 is frozen. Ice caps, glaciers, which is not going to be usable to us unless we melt it down. 30% is your groundwater. So if you live outside the village of Rhinebeck, you have groundwater. That's where you have a well. You pull your water from there. So that's 30% of all that fresh water. And then 0.3%, 1/3% of all the fresh water is surface water, which then gets broken down into this column. So you have 3% of all the water is fresh, 1/3 of that 3% is surface, and then the surface water is broken into this column. 2% is your rivers, like the Hudson and Mississippi, etc. 11% is your freshwater swamps, and then 87% of all the fresh water is in your lakes. So that's 0.3% of 3%. So it's a very small fraction is actually fresh water on the surface. Very small percent. Then you take some specifics. So if you look like up here, for example, you have your 5 Great Lakes. That's 20% of all the fresh water on Earth. So it's in these 5 Great Lakes: Superior, Michigan, Huron, Ontario, and Erie. Over here is Ontario, which is on the western side of New York State. You've got where my wife went to college. She went to Oswego. Put a little dot. You got Rochester right about here. You got Buffalo, which is kind of in between Ontario and Erie. Anyway, Ontario has a depth of average depth 283 feet, length about almost 200 miles. Erie is your shallowest Great Lake, 62 feet deep, 240 miles long. Huron over here on the eastern side of Michigan, that would be almost 200 feet deep and 200 miles long. Michigan, you got Chicago, put a dot, there's Chicago, about 280 feet deep on average and 300 miles long, so that's pretty long. And then the biggest Great Lake is Superior, way up here, and they call this the UP of Michigan, which I guess, what do they mean by UP? It's the Upper Peninsula, right? But Michigan's broken up into 2 parts. You got this peninsula of Michigan and then this peninsula of Michigan. So that's the Upper Peninsula as opposed to the Lower Peninsula. Anyway, Michigan is, or Superior, I should say, is 489 feet deep and 350 miles long. So of the 5, you take the 5 Great Lakes, that's almost 1/5, right? 20% of all your fresh water is just in those Great Lakes. Another 20% or 1/5 of all the fresh water on Earth is in a lake in Asia. It's called Lake Bakala. And I'll show you a picture of that. So you're talking almost half, right? 40% of all the fresh water on Earth is in 6 lakes. Your 5 Great Lakes and your Lake Bakala over in Asia. This is a picture to show you where Lake Bakala is. So if you look at this top picture, you've got Russia, you've got China, you've got Mongolia down here. Lake Bakala is right there, just along the southern portion of Russia. It's a very long, narrow lake, runs kind of north-south, so this is it right here. It runs about 400 miles from top to bottom. Now the depth is pretty impressive. It's 2,442 feet. So if you go back for a sec, right? Superior was almost 500 feet deep. So this lake right here, Bakala, is about 5 times deeper than Lake Superior. So that's a major source of fresh water for many areas of Asia over there. So that's a pretty important lake for them. Atmosphere. So the atmosphere is your gases that surround the Earth, and it is in layers. Now this word you'll see again when we get to rocks, especially sedimentary rocks. If you have rock like sandstone or shale, they tend to form in layers. They call them strata. So strata is a layer, and if something is layered, they call it stratified. So the atmosphere is actually stratified or layered. It's broken up by temperature zones. This term will come up on a question, especially on a Regents, and it always throws students off because they don't know where the heck to look in the reference table, which it is in the reference table. We're going to look at that right now. So if you could, take a minute, pause the video, and pull out your ESRT and go to and you're going to need this for the assignment this week. Go to page 14 in your ESRT. So take a second, pause this video, and then pull out that ESRT and go to page 14. Okay, hopefully you did that. And so if you have your ESRT out, here's temperature zones. Let me use a different color. Way up here at the top. there's the term temperature zones, which kids always miss this. And they say, Mr. Rocco, I don't know what the heck they're talking about. Temperature zones. What temperature zones? There's 4 of them. Troposphere, Stratosphere, Mesosphere, Thermosphere. Those are the 4 temperature zones. Because down here, you see this? It says temperature. You've got a temperature graph. Let me clear this. Let's use blue and highlight the temperature graph. It goes zigzags here, there, oops, there. I'm doing this with a mouse, sorry. And there. There's your temperature graph. So those are your temperature zones. In the troposphere, that's the lowest layer. This is the surface. The temperature goes down. So if you see here, let me clear this. Right at this point, I'll put a dot. At the surface, temperature, average temp, this is average, is 15 degrees Celsius. Then you get to the top of the troposphere, and the nice thing they do with this graph, they give you dotted lines. You get to the top of the troposphere right here. I'll put another dot. You follow that down, the temperature is negative 55 degrees Celsius. So we went from plus 15 to minus 55. So the temperature dropped off dramatically as you go up the troposphere. Now that's common sense. If I asked a student, hey, what happens if you go up a mountain? You go up high elevation. Well, it gets colder. That's why it gets colder, right in this section. However, now once we leave the troposphere and we go into the stratosphere, that's the next layer, it starts at minus 55. I go this way. When I get to the top of the stratosphere, I'll put a dot here now, and then follow that dot down that dotted line. Notice what happened. The temperature actually warmed up. It was at negative 55. But now it came back up to 0. So the temperature actually warmed in the stratosphere. Why? That question comes up usually as I talk about this every year. They say, why does the temperature get colder? Most kids know, hey, it gets colder when you go up a mountain. Yep. But why does it get warmer when I get into the stratosphere? Ozone. So in the stratosphere is a layer called ozone. Ozone is what protects us from ultraviolet. It absorbs ultraviolet. So you've got UV rays, ultraviolet A, ultraviolet B. Those are your common ones. Ozone traps or soaks up that ultraviolet and actually takes that ultraviolet, turns it into heat. So that ultraviolet turns into heat, which then causes the stratosphere to get warmer, not colder. That's why it gets warmer in the next layer. Then you go into the mesosphere. Notice what happens in the mesosphere. Let me clear this. You start here, which was at 0, but notice it does like the troposphere. It gets colder, 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 and you get to the top of the mesosphere, you're at this point, and now you're even colder than you were at the top of the troposphere. You're now negative 90. No ozone up here. Nothing to trap any kind of heat. So you lose all your heat in the mesosphere. So it gets extremely cold. And then the thermosphere, notice what happens to the temperature here. You start at negative 90. And then, when the graph kind of fades off here, you get up to the top. You're not even at the top of the thermosphere. As you can see, it says extends to 600 kilometers. This graph only goes up to 120 kilometers. So at that point, though, if I was to take this spot right here and come straight down, you're well over 100 degrees Celsius, which again, if you know what 100 Celsius does to water, right, makes it boil. So you're over the boiling temperature at 120 kilometers up. Why? The atmosphere is getting much, much thinner, right? Your most concentrated gases, your oxygen, all the things, the ozone, the things that protect us are down here in the bottom part of the atmosphere. As you go up higher and higher, this very, very thin, and again, I'm using a mouse, sorry, thin atmosphere up here that's not going to protect you from the sun's energy. So those sun's rays really cause the temperature to skyrocket up here in the upper parts of the atmosphere. Okay. Now, so those are your temperature zones: troposphere, stratosphere, mesosphere, thermosphere. They're broken up by what's called a pause, right? Think about pause. If you talk and then you pause, right? You stop. So it's a boundary, or in the first topic, we called that an interface. I use the example, I said the door is an interface, or the windows are an interface. So you have these imaginary dotted lines, just like when you cross from New York to Connecticut, right? A state boundary, it's just an imaginary boundary. So you have the troposphere. When you get up into the top part of the troposphere, you hit what's called the tropopause, and that then takes you into the stratosphere. and then you have the stratopause, again, another boundary. And then you hit the mesosphere, and then you hit the mesopause, and then thermosphere, and up you go. There's a scale over here. Be very careful with the scale. It's the altitude scale telling you two things: kilometers on the left, miles on the right. You might want to add this to your reference table. I would do that now. The scales are different because miles and kilometers are different. On the left side, you see this is 0 kilometers, then it goes 1, 2, 3, 4. That means each of these count by tens. So I would stick a 10 over here on your ESRT. On the right side is miles. This is 0, then it goes 1, 2, 3, 4, 5. That means these count by fives. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, etc. So each increment on the right is 5 miles each. Each increment on the left is 10 kilometers each. There's going to be a few questions on your assignment today, or that you do, if you don't do today, but this week, that will ask questions like that. So, for example, let me clear this. It might say, at what altitude is the mesopause in miles? Be careful with the question, right? Make sure you give the correct. They're going to try to give you that distractor I talked about in class. If you come to class about a distractor is just trying to get you off tangent because you're not paying attention to the question. So if they said, what is the altitude of the mesopause in miles? You come across mesopause and you can see clearly the answer is 50 miles. Just make sure you're on the miles side. Guess what else they're going to give you as a choice? You guessed it. They're going to give you 80 because they're going to bet on the fact that a kid reads this and went, oh, it said miles, and I picked the left side and went with kilometers. So they're going to try to trick you and give you something like that. So just be careful. They might ask you, what altitude is the stratopause in miles? So you'd have to come across, and that's why it's important to know the scale. So here's the stratopause. Notice you're slightly above that mark. So if you remember, these count by fives. 5, 10, 15, 20, 25. This is 30. So you're looking at a little bit above, maybe 32, somewhere in that region. In kilometers, it would be what? 50, right? Because this is 10, 20, 30, 40, 50. So it's 50 kilometers, 32 miles. So again, be careful what they're asking you for on a regions question or any kind of question. All right, you also have over here a pressure chart. Pressure is measured in a couple different units. You can measure it in square or inches, pounds, and they use what's called ATM. Not ATM like a place you go get some cash. ATM stands for atmospheres. So this graph's a little tricky. It starts at the highest pressure down here. So the graph starts right here. I'll put a purple dot. Down on the ground is the greatest pressure. It's 1 atmosphere. As you go up, the pressure line isn't going up. Like usually I'll show the students, I'll say, oh, it's increasing. No, it's going this way. But notice the way the graph's heading. As you go up, this line is getting closer, moving this way. It's moving toward the left, which is heading closer to 0. So the pressure is actually going down as you go up. Even though the line is drawn upward, it's heading toward 0. So it's 1 atmosphere at the surface. When I get to this tropopause right here, if I put a dot here and I come down, notice where I am. This would be what? A quarter, a half, 3/4, 1. So this is a quarter of an atmosphere, half an atmosphere, 3/4 of an atmosphere, 1 atmosphere. So on the ground, you're 1 atmosphere. When you get to the top of the troposphere, right at this first dotted line, you already are at 1/4 of the pressure that it was on the ground. Now you probably know pressure, that's what happens when you go up, right? Go up a mountain, go up high elevation, what do you notice? Your ears, right? Your ears will pop to adjust to the pressure. Right? Go up in an elevator, go up a tall skyscraper. Anytime you go up in elevation, you feel that popping in your ears, or come down, you feel it. So when you leave one altitude and go either up or down, you feel that ear pop. That's what happens based on this graph. So the pressure is only 1/4 the amount of pressure once you get up to the top of the troposphere. Now, if you keep going, that's a quarter. It's very hard to tell. The pressure of the graph, notice it keeps heading toward the left, and eventually when you get to the top of the stratosphere, you're right in this area. It looks like it's right on the line. It's not a good graph. It's basically hugs the line the rest of the way. There's some pressure, but you're talking now, you're not a quarter of the pressure. You might be at 1/10, 1/20th the pressure. It's a very small fraction of pressure. And then it stays there. Notice the line looks like it's right on zero as you go up. But it is some pressure, but it's very, very, very little pressure as you go up. Then you have your water vapor, water in the gas phase, which makes clouds. Water vapor is what makes, here's my sketch of my cloud with a mouse, right? So, and then you get rain, and you get snow, and all kinds of precip. So water vapor is what makes clouds. The water vapor graph's a little tough to see. It actually starts like right here. It doesn't go to 40. It actually starts at around 30, and this is in grams per cubic meter. So you're measuring the concentration or the density, right? The concentration of the water vapor. It's more concentrated down here. Again, as you go up, yes, the line goes up, but notice the graph is heading, again, like this pressure graph, heading to the left, heading towards zero. So that by the time you get to the top of the troposphere, you're down to, again, very small amount. And then in the lowest part of the stratosphere, there's a little bit of water vapor still left, but only in the very, very low part of the stratosphere. This line ends here, and if you come over this way, you're talking right about here, I would say. So I'm doing the best I can make a straight line. Yeah, that wasn't bad, Mr. Rocco. That's about 5, 10, maybe 15 miles up at the most is where you're going to see water vapor. Meaning, once you get above 15 miles above the Earth, up in this area, and as you go up, there's no more water vapor, meaning no clouds, no weather. Think about a plane. If you've ever flown in an airplane, right, you're usually flying at your cruising altitude. You're kind of above the weather. The clouds are below you. Okay. So that's this chart. Very important chart. You've got your three scales, your temperature graph, your pressure graph, and your water concentration. Again, be careful with the two altitude scales, kilometers and miles. And again, anytime they ask you a question about temperature zones, these are your four: troposphere, stratosphere, mesosphere, thermosphere. All right, so hopefully you still have your reference table out, page 14. Let's just go through this. It says by what percent of the crust, by mass, what percent of the crust is oxygen? And that actually comes off page 1 in the reference table. So let me find my reference table. Give me 1 second. There it is. All right, so if you go to the SRT, and this chart you'll use for the assignment part of it. Some of the questions come off there. So what, by mass, what percent of the crust is oxygen? So you look up crust and then mass. Right away the key words there. Crust, mass, what percent is oxygen? Right there. Pretty easy. 46.1%, and that should be behind that box. Yes, it is. What is the inferred, remember, guessed, average density of the outer core? That's in the reference table, but not on this chart. That was a chart I went over with you a little earlier. That's on page 10. So let me go to that chart. Oops, right here. And it said, let me go back, it said outer core. Yep, outer core. So the outer core is right here. You find outer core. And then you get your densities are over here on the right. There's my number I'm looking for right there. A range, 9.9 to 12.2. Oops. So I go to that, and there it is. How many miles up is the mesopause? We just did that. Let me go back on this set of notes. It's there. How many miles up is the mesopause? So I find mesopause. I shoot across to the left. Miles is 50, right there. Go back to that. What is the lowest layer of the atmosphere called? So lowest layer or temperature zone. Go back to the previous page, right? It's called the troposphere. It's right there. That should be good. And water vapor decreases to 0 at approximately how many miles up? So again, that was on the chart. We just went over that. So here's where it turns to 0. And again, if you come across, it's between closer to the 15 miles. Oops. go back. About 15 miles up. This just talks about the stages of our atmosphere. So basically, I'll just kind of read through this. It says the original atmosphere was primarily helium and hydrogen. So if you go back to the beginning of the solar system and the beginning of Earth formation, there was no oxygen in the beginning. It was hydrogen helium, which happens to be the gases that stars are made of. Our sun is made of hydrogen helium. 3.5 billion years ago, volcanoes release steam, CO2, carbon dioxide, ammonia. This leads to atmosphere number 2, which was primarily CO2, carbon dioxide, and water vapor, a little bit of nitrogen, no oxygen. The second atmosphere had 100 times as much gas as the current atmosphere. So that second atmosphere was a very choking atmosphere. So original atmosphere, hydrogen, helium. 3.5 billion years ago, now we're talking carbon dioxide and water vapor. No oxygen, but very thick atmosphere. It says here, believe that the greenhouse effect, right? CO2 is a major greenhouse effect. You know that. That's going to cause our temperatures to really increase. And then it says during the next few million years, water vapor condensed to form rain in oceans, which began to dissolve that CO2. 50% of the CO2 would then get absorbed into the oceans. One of the earliest types of bacteria were cyanobacteria. So these bacteria, like a plant, right, is going to use that carbon dioxide, okay, to produce oxygen. Fossil evidence indicates these bacteria existed 3.3 billion years ago and were the first oxygen-producing phototrophic organisms. They were responsible for the initial conversion of our atmosphere from an anoxic state to an oxic state. So we went from no oxygen to now having oxygen. Oceans in the beginning were not blue. They were green. They got their blue as more oxygen started to develop. And then what happened is, as that excess oxygen was in the oceans, that oxygen that eventually came out of the water started to go into the atmosphere, and that's what sort of supplied our atmosphere with the oxygen that we needed. It says, being the first to carry out oxygenic photosynthesis, they were able to convert the CO2 into oxygen, which played a major role in oxygenating the atmosphere. Tough word. Photosynthesizing plants would later evolve and convert more CO2 into oxygen. Over time, the extra carbon became locked up in our fossil fuels. So carbon ended up in a lot of your rocks, which ended up in your fossil fuels, carbon-based, right? Oil and petroleum-based products. As oxygen was released, it reacted with ammonia to release nitrogen. In addition, bacteria also converted ammonia into nitrogen. As more plants appeared, the levels of oxygen went up, and the CO2 levels went down. And that's what led to our current atmosphere, which is at 78% nitrogen, 21% oxygen. Again, these numbers are right on the front of your reference table. So we went from hydrogen, helium, step 1, to a lot of carbon dioxide in atmosphere 2, to now nitrogen, oxygen, atmosphere number 3. Does that mean we're done with our atmosphere development? No, we know that. But at this point in Earth's history, that's where we're at. We're in our third stage. This just talks about the different atmospheres, so I'll read these over quickly. And I kind of touched on some of this. The troposphere, again, is our lowest layer of the atmosphere. Goes up about 10 kilometers, 6.2 miles, or 33,000 feet. Humans live in the troposphere. All weather occurs in the troposphere. Most of your clouds, again, appear here because 99% of water vapor is in the troposphere, which we went over a little while ago. Air pressure goes down, and temperature gets colder as you go higher into the troposphere. The next layer is the stratosphere. Stratosphere goes from the top of the troposphere to about 50 kilometers, or about, we said, 32 miles. The infamous ozone layer is found in the stratosphere. So that question will come up quite often on the Regents. Where is the ozone layer found? It's in your stratosphere. Ozone absorbs the high energy ultraviolet light, converting it to heat. And that's why it gets warmer. Unlike the troposphere, again, the stratosphere gets warmer the higher you go. That trend of rising temperature with altitude means the air in the troposphere lacks turbulence and updrafts of the troposphere beneath it. Commercial passenger jets fly in the low stratosphere, partly because this less turbulent layer provides a smoother ride. The jet stream flows near the border between the troposphere and the stratosphere. So yeah, your planes, they're usually up above 33,000 feet. They're at 34, 36, 38, 40,000 feet. That's because it's a much smoother ride up there. So you're not hitting that turbulence that you would hit if you stayed down in the lower part in the troposphere. Mesosphere. Above the stratosphere is the mesosphere. It extends up to a height of, again, about 85 kilometers or 53 miles above our planet. Most of your meteors burn up in the mesosphere. You might see what they call a shooting star. They're burning up, when you see that shooting star, in the mesosphere. That's how high up they are. You're talking over 50 miles above your head. Unlike the stratosphere, temperatures again get colder as you go up through the mesosphere. The coldest temperatures on Earth, again about negative 90 Celsius or negative 130 Fahrenheit, are found near the top of the mesosphere. The air in the mesosphere is far too thin to breathe. Air pressure at the bottom layer is well below 1%. Again, it's a very small fraction of air pressure and continues to drop as you go up. And then your thermosphere. The layer of very rare air above the mesosphere is called your thermosphere. High-energy X-rays and ultraviolet from the sun are absorbed in the thermosphere, raising its temperature to hundreds or at times thousands of degrees. So collecting all these X-rays will cause the temperature in the thermosphere to really skyrocket. However, the air in this layer is so thin that it would feel freezing cold to us. In many ways, the thermosphere is more like outer space than any part of the atmosphere. Many satellites actually orbit Earth within the thermosphere. Variations in the amount of energy coming from the sun exert a more powerful influence on both the height of the top of the thermosphere and the temperature within. Because of this, the top of the thermosphere can be found anywhere from 500 to 1,000 kilometers above the ground. Temperatures in the upper thermosphere can range from 500 Celsius to 2,000 Celsius, 3,600 plus Fahrenheit. The aurora, or the northern lights, and the southern lights occur in the thermosphere. And then again, these two layers wouldn't worry so much about. You have what's called the Exosphere, and you have the Ionosphere. It says, although some experts consider the thermosphere to be the upper layer of our atmosphere, others consider the Exosphere to be the actual final frontier. As you might imagine, the air in the exosphere is very, very, very thin, making this layer even more space-like than the thermosphere. In fact, air in the exosphere is constantly through very gradually leaking out of our atmosphere into outer space. There's no clear-cut upper boundary where the exosphere finally fades away into space. Different definitions place the top of our exosphere between 100,000 kilometers and 190,000 kilometers, which is 120,000 miles above the surface. The latter value is about halfway to the moon. So, yeah, a lot of debate over how far out does our atmosphere really go, technically. And then the ionosphere is not a distinct layer like others mentioned. Instead, the ionosphere is a series of regions in parts of the mesosphere and thermosphere where high-energy radiation from the sun has knocked electrons loose from their parent atoms and molecules. The electrically charged atoms and molecules that are formed in this way are called ions. So an ion, you might gain an electron or lose an electron, giving the ionosphere its name and endowing this region with some special properties. And let me pause. Okay, so this was a pretty long video. I apologize. I do have this little clip. I might post it on Canvas. You don't have to watch it, but it's kind of cool. Several years ago, there was a guy named Felix Baumgartner. He did a jump out of the stratosphere. He did a free fall. You might have seen this already or heard about it. It's a 8-minute video, I think. I'll post it separately. Again, it doesn't have anything to do with the assignment, but it is kind of cool to watch. And you'll see him. He goes up into the stratosphere, and he sets the record for the highest free fall. And it was like a big stunt that he did. It was sponsored by Red Bull, the Red Bull drink. And I'll post that on Canvas so you can actually watch that. And again, it doesn't have anything to do with the assignment, but it's kind of cool to watch. All right, that's it for this video. Sorry it went a little long, but that'll be the only video this week. And then do that assignment. It's called Spheres of the Earth. And then don't forget to do the test and also do the finish up that graph lab. Okay, hope you have a good week, and I will talk to you soon. Bye.